vehicle dynamics. Here, we will analyze design, the conditions and factors required for vehicle design from the perspective of dynamics. For this course's compressed air racing, we can consider a more comprehensive and scientific design thinking, the resistance that the vehicle encounters during motion. From the following image, we can see that during the vehicle's motion, it will sustain rolling resistance from the road, air resistance from the incoming air, acceleration resistance from the weight of the car, friction given to the car from the unevenness of the ground surface, or grade resistance from a slope. All these forms of resistance are limiting factors that we must take into account in our vehicle design since they will cause the vehicle to not be able to perform better. Therefore, the design thinking for vehicle optimization is to reduce these resistances and improve the vehicle's driving performance, which is the most important scientific-based assessment for vehicle design thinking. The resistance generated by the tires rolling on the ground. Rolling resistance refers to the frictional resistance generated by the deformation of the tires against the ground. When the wheel is rolling, regarding the contact area between the tire and the ground under the pressure of the vehicle's weight, the wheel's circumference is under the process of continuous compression, deformation, and recovery. The tire and the rubber molecules generate friction. The heat generated by friction diffuses to the atmosphere, which consumes the vehicle's output power, generating rolling resistance. When the vehicle moves at low speeds, rolling resistance is the main source of the vehicle's power loss. The resistance generated by the car body against the air. The formula for air resistance is ρ times A times V squared times CD divided by 2. Ρ represents air density, A represents the area of the frontal projection of the car. V squared is the car's velocity squared, and the air resistance coefficient is CD. The product of these values then divided by 2 is the influence of the air resistance on the vehicle. From this physics formula, the windward area of the vehicle body is proportional to the air resistance, and the velocity squared will increase its influence. From this, we can understand that at high speeds, air resistance becomes an important factor in the vehicle's driving resistance, affecting the vehicle's maximum driving performance. When the car is moving, it produces relative displacement to the surrounding air, and the air in front of the car is constantly squeezed out, causing windward air pressure. Because the airflow at the back of the vehicle cannot keep up with the speed of the vehicle, especially at high speeds, this causes a certain degree of vacuum, which generates vortex that creates suction. Also, air has a certain viscosity, which will produce friction with the surface of the car body and create resistance. The pressure, suction, and friction are forces of the air that impede the movement of the car and are collectively referred to as air resistance. From the formula in the lower left graph, we can see that the higher the speed of the vehicle, the higher the percentage of influence of air resistance. According to a comprehensive test of the European Union, at an average speed of 32 kilometers per hour, air resistance accounts for about 1/4 of fuel consumption. However, when the vehicle speed is increased to 90 kilometers per hour, half of the fuel or energy will be consumed by air resistance. In a compressed air racing car design project, the car's speed will be very fast. Therefore, the impact of air resistance on the vehicle design, relatively speaking, becomes more significant. Here we have a comprehensive analysis of the conversion of the power into kinetic energy for the compressed air racing car. When we start the cylinder of the compressed air racing car, according to Newton's second law of motion, acceleration is equal to force divided by mass. The force provided by the high-pressure steel cylinder itself is fixed, and the weight of the vehicle itself is the key to the impact of the initial force on acceleration. As the vehicle's acceleration gradually increases, it must overcome the car's weight and the rolling resistance caused by the ground. Rolling resistance will be the greatest resistance faced by the vehicle at low speeds. At this time, the efficiency of our wheel and axle system in operation will be the most important design consideration of our vehicle design. When the acceleration reaches its maximum value, the kinetic energy of the vehicle is at its maximum. According to the physics formula, K equals m times v squared divided by 2, when the acceleration increases to its maximum, the vehicle's velocity is also at its peak. The vehicle's weight multiplied by the square of vehicle speed will be an important energy for the vehicle's endurance. As speed gradually increases, the air resistance will be the biggest resistance faced by the vehicle, which formula is, as mentioned before, rho times A times V squared times CD divided by 2. The improvement of vehicle speed, the design of the vehicle body, and driving stability will be major design considerations for the improvement of endurance and decrease of speed reduction. The analysis of the compressed air racing car's power and driving kinetic energy is a complex dynamic variable. Here we use these physics formulas to serve as assessments for some design considerations. They provide a correct logical thinking for vehicle design. Applying theory-oriented design thinking is an important learning content in our high school living technology course, and the conceptual knowledge of vehicle dynamics provided here will be an important theoretical basis for our design thinking. Hello everyone, here I'll be doing an introduction to advanced vehicle dynamics. In this advanced learning content, we will make a further introduction to the dynamics of vehicle control. Let me introduce you to a few concepts first for all students to understand. Concept 1. The vehicle's original dynamics can be greatly affected under circumstances with dramatic changes in road variables and driving conditions such as steering and braking. For example, let's take a look at the lower right picture. When this F1 racing car turns in a corner, the vehicle will produce a huge centrifugal force. The inner tire of the turning wheel will reduce its contact pressure with the ground due to the centrifugal force. At the same time, if the F1 racing car has drastic handling situations and frequent braking, the inertia change of the vehicle will also be great. These changes in centrifugal force and acceleration will cause the car to endure immense force changes on the track, which will cause some changes in the handling performance and safety performance of the vehicle and need to be effectively controlled. Vehicle design shall be very demanding on vehicle control performance, so the study of dynamics is a very important concept in vehicle design. Concept 2. Vehicle's handling performance. Tire is the greatest reliance on which the vehicle can maintain the safe and effective driving force on the road. Therefore, it is very important for the tire to maintain positive pressure and friction, which is related to the driving safety and the stability of handling performance of the vehicle. As we can see from the lower left figure, the vehicle has an overall of 6 axial degrees of freedom. Each tire is an independent entity, which maintains an appropriate amount of pressure with the ground at all times under various dynamic conditions to maintain its driving and safety. Under such conditions, the design of the fixed suspension system of each tire and the car's body structure so that the tire maintains the appropriate positive pressure is the biggest goal of the whole control system design. Analysis system of dynamics. Concept 3. The analysis of dynamics requires 3 system coordinates. The side of the car is the x-axis. You can see that the direction of the mouse is the direction of the x-axis. The width of the car is the y-axis, which is the direction you see right now shown by the mouse, which represents the y-axis. The height of the car is the z-axis. You can see that the direction shown by the mouse is the z-axis of our car. The change of the force exerted on each axis will produce different dynamic changes of the vehicle. For example, the dynamic changes of the x-axis will produce some rolling phenomena. The influence of the dynamic changes of the y-axis on the vehicle will produce pitch dynamic changes. The dynamic influences of the z-axis will produce yaw dynamic changes, resulting in changes in vehicle stability and handling. For a vehicle, these yaw, pitch, and yaw should be as small as possible. The driving of the vehicle should be done in a stable condition so that the passengers have better comfort and safety. Analysis principles of vehicle dynamics. Concept 4. The analysis principle of dynamics is mainly based on the concept of conservation of energy, that is, all the input forces are equal to all the driving reactions of the vehicle's output. Using a mathematical model to represent the vehicle, all the horizontal dynamics of this model that mainly affects the vehicle is in the handling safety. The effects of vertical dynamics of the mathematical model mainly affects comfort of the passengers towards the vehicle. For these principles, we can use simple mechanical formulas to make design thinking judgments, to make design thinking assessments and applications. These principles will be very helpful in the conceptual clarification and design decision making. From the 4 important principles of vehicle dynamics stated previously, in order to cope with complex driving changes, vehicle design considers many vehicle dynamic design factors in suspension, shock absorbers, and steering system design. Complex mechanisms and electronic control systems are designed to stabilize the force variations of these driving conditions so that handling performance and safety can be improved, such as the dynamic effects of centrifugal force on the tires and on the road surface mentioned earlier. When the vehicle is turning, the tire of the inner wheel will be pulled away from the ground by the centrifugal force, resulting in insufficient positive pressure. At this time, the inner wheel can easily lose friction. In serious cases, it can cause the vehicle to roll over. Therefore, for the responsive design measures of modern car manufacturers, anti-roll mechanisms are designed on the vehicle's chassis, such as the use of anti-roll bars, suspension system with adjustable damping coefficient, or the use of electronic-controlled methods such as the DSC dynamic stability system to improve the stability of vehicle driving so as not to roll over when turning corners. Tire specs and driving characteristics. The tire specs factor which affects driving characteristics most directly is the flatness ratio. Flatness ratio is the percentage of the height of the tire H divided by the width of the tire W. In general, trucks will use tires with the higher flatness ratio, such as this wheel, designed on the left side of this picture. Certain cars will use moderate flatness ratio tires, and racing cars or sports cars will use wide tires with low flatness ratio. In terms of load performance, tires with high flatness ratio have a better carrying capacity, while the tire with low flatness ratio will show better characteristics in sports performance. Such a concept can be assessed from the cross-sectional shape of the contact between the tire and the ground. For example, the contact area between a tire with a high flatness ratio and the ground will be long and narrow-shaped. Because it is long and narrow-shaped, it will have a better straight-moving performance, which also means that it would be more fuel efficient and withstands load. This long and narrow-shaped tires under certain driving situations such as the action of centrifugal force can easily have its cross-sectional area reduced, causing a loss in its contact area. On the other hand, track-type racing cars using tires with low flatness ratio and the contact area with the ground has a widened cross-section. When such cross-section turns, there will still be plenty of area contacting the ground under the traction of the centrifugal force, so its handling performance will be better. However, in terms of straight driving and carrying capacity, compared to tires with high flatness ratio, they will be relatively inferior. Design of vehicle steering response and shock absorption function requirements. The vehicle's design must allow the wheels to have enough upward and downward motion, rotation, and swinging space so that the vehicle can exert its steering and shocking absorption functions. For such control mechanism, we need to design a steering knuckle, tie rods required for steering, and a multi-link control suspension system, including the spring and shock absorber so that such design can meet the driving requirements of the vehicle's steering and shock absorption function. The design requirements of the steering system is as seen from the right figure. When the vehicle is steering, the angle of rotation of the inner wheel is greater than the outer wheel. This must fulfill a principle known as the Ackermann steering principle. As seen in the design of the steering mechanism in the left figure, we will push and pull this tie rod during the steering process. The tie rod and the steering knuckle will be a trapezoidal four-link design, which will cause the steering knuckles on both sides to rotate at different angles when pushing and pulling the tie rod, so that the steering angle of the inner wheel will be greater than that of the outer wheel. The goal of this design is to allow the smoother steering of the vehicle. Each tire is based on the same instant center of rotation, which is the intersection of the rear wheel axis and the perpendicular lines of the bisection line of each wheel. The angle design of the steering knuckle, the center line of the left and right wheels, will intersect at the center point of the rear wheel axis. This is designed to allow the steering system to get good control. For the orientation of the wheels apart from the design of the steering mechanism, the wheels are adjusted to a fixed angle in the structure of the vehicle to make the vehicle more stable. This angle includes the camber angle, toe angle, and caster angle, among which the most important one is the camber angle, which is defined as shown in the right figure. According to the center line of the tire, if it inclines outwards, it is a positive camber. If it inclines towards the car body, it is a negative camber. Usually, the adjustment angle is usually set while the car is at an empty state. When carrying passengers or loads, the tires of the vehicle will be restored to the correct angle, so that the tires can get the maximum contact area when driving. What was mentioned before was the wheel positioning for regular cars. What is different for the wheel alignment of a racing car? From the picture on the right, you can see a clear example. Racing cars mostly need fast response for intense corners and frequent speed conditions, so the camber angle of the car will be designed to be negative to counter the centrifugal force that lifts the tire off the ground and causes loss of friction. And a smaller caster angle design allows an agile steering. The racing car's suspension system is designed based on the center of gravity of the vehicle, so that the axle line of the suspension system is designed according to the inclination of the center of gravity. This way, when the driver sits on the racing car, he will not suffer great burden to his body because of the drastic change of acceleration.